Hey everyone, we've got a lot to cover today, so let's go. Alright, first thing we're going to cover wave speed, wave transmission, and sound. Like, what is sound and all of that stuff. So for wave speed, alright, for the speed of a wave moves at a certain speed. Like we discussed already, that it's moving energy. It moves from here and it can move across the medium. And since it's moving, it has, again, some non-zero speed. Now, waves, for the most part, will move at a constant speed. So we can use a nice simple equation for this, v equals d over t. But for the most part, that's going to be less helpful because it's not in terms of like the wave things that we talked about, like frequency, wavelength, that kind of stuff. But it's a good starting point. So we can talk about the speed of a wave using v equals d over t. It'll show up every once in a while, but for the most part, we're going to use the different equation, which we're going to derive right now. So here's what I'm going to do. Let's say we've got a wave, I don't know, like this. And actually, you know what I'm going to do is I'm going to change color. Everything that's going to be in this wonderful pink color, you do not have to write down. So you don't have to write down anything that's in the pink color. But this is where this equation is going to come from. If we take we got v equals d over t, but it would really be more helpful, since we're talking about waves, to put this in terms of like wave type values, like wavelength, frequency, that sort of stuff. So let's take a distance that a wave could travel, like, I don't know, from here to here. The reason I'm going to choose that is, see how this is the length of one complete wave? So for the distance, what I'm going to do is I'm going to plug in the wavelength, because it's the length of one wave. That's like a wave type value that we've discussed. And then for the time, well, what's the time it takes for one complete wave to go by? We have a special word for that time. It's called period. And that was a capital T in the equation. So I'm going to replace that lowercase t with a capital T. I know it seems like a small difference, but it doesn't have a special significance when we talk about waves. Now I'm going to rewrite this as I'm going to take that divided by t, and I'm just going to write it on the side as 1 over t. And then I'm going to leave that wavelength where it was. And I know that that seems like a strange thing to do, but see this 1 over t? I hope that looks kind of familiar from lesson number 1. 1 over the period is equal to the frequency. So what I'm going to do is I'm going to replace that 1 over t with f, the frequency. And now we have our wave equation, the equation for the speed of a wave. This is actually the last equation we're covering this unit, so we've covered all of our math already. Just to sort of isolate this, v equals d over t works, but for the most part, the equation we're going to use is v equals f lambda, which again, we made a couple substitutions and showed that they're equivalent to one another. The reason we prefer this is it's in terms of like wave things, frequency, wavelength. Those are wave type values that we could do and measure. So we kind of like this because it's just a little bit more, stays within itself. Just writing out what everything means. F stands for frequency, just like it did before. And we measure frequency in hertz, which remembers the waves per second hertz. Waves per second. Lambda stands for the wavelength, which we measure in meters. And then v stands for the velocity of the wave, which, just like all of our velocities this year, will be measured in meters per second. And this equation, it's kind of as simple as it looks. I'm going to do number 20. We'll do 20 together. I'll have you try the rest on this page, and then we'll move on. What is the speed of a water wave with a wavelength of 10 meters if it has a frequency of 0.15 hertz? Okay, we want the speed. That's v. We know the wavelength is lambda. We've got a frequency f. There's just not a lot of equations for this topic. There's t equals 1 over f, and there's v equals f lambda. The frequency is measured in hertz, so it's the 0.15. The wavelength is 10 meters. Alright, 0.15 times 10 is 1.5 meters per second. Cool. And that's our answer. So a water wave, like you can see it moving across the ocean, right? How fast is this water wave moving? 1.5 meters per second. Try the rest of these. 21, 22, and 23. Again, pause the video, give it a shot. I'm going to go through them all. You can kind of check your answers against mine, and if you need an explanation, that's what I'm about to do. But again, pause it, try it on your own first. Alright, hopefully you tried it on your own. What is the frequency of a wave with a wavelength of 500 meters if it travels at a velocity of 25 meters per second? Alright, so we're solving for F. We've got wavelength lambda, V. Again, we've only got two equations for waves, so this might get a little repetitive. We know that the velocity is 25 meters per second. We're solving for F. We know that, we know that the wavelength is 500 meters. Let's put this in our calculator, which I should have done ahead of time. And when you do that, I got 0.05 hertz. So F equals 0.05 hertz. Or 1 over 20, I think 120. 22, a beam of light has a wavelength of 4.5 times 10 to the negative 7 meters in a vacuum. What is the frequency of this light? I gave you a nice hint here. The speed of light is a constant. Well, anytime something is a constant, I will assume you know what to do with that, and what you should do with that is look it up in the reference tables. Oops. Thought I had that open. I apologize. All right, your list of physical constants is here, and the speed of light is this third row down, 3 times 10 to the 8th meters per second. That's a big number, but light is famously very fast. So, we can use our V equals F lambda equation. V is 3 times 10 to the 8th meters per second. Equals F lambda. I think we're solving for the frequency of light. Light has high frequencies, so you might have gotten a big number for this, and that's okay. It also has very, very tiny wavelengths. 4.5 times 10 to the negative 7 meters. Okay, it looks like we're going to have to just divide across here, and I got a frequency of 6.67 times 10 to the positive 14 hertz. That's 6.67 times 10 to the 14 hertz. My final answer there. So again, a high frequency, but light has high frequencies. So there you go. Alright, 23. The diagram below shows a periodic wave traveling through a medium. The frequency of the wave is 2 hertz. Find the period of the wave. Okay, we're actually going to deviate from our V equals F lambda that we just did over and over and over again, because I tried to make a big deal out of this on lesson number 1 for this topic. If you know frequency, you can find period, always. You don't need anything else, because we have an equation with those in it. T equals 1 over F. Sorry about that. T equals 1 over F. The frequency I said pretty clearly was 2 hertz. So equals 1 over 2. Man, this is not working for me today. 1 over 2 hertz. 1 over 2 hertz is equal to, I think, 0.5 seconds? Yeah, it looks good. 0.5 seconds works for this. I'll spell out seconds because that just looks like another 5. Cool. Now we want the speed of a wave, and we have an equation for the speed of a wave. Only 2 equations for this unit. So if we're doing our calculations, you don't have to look too far here. So for the speed of the wave, V equals F lambda. Alright, we're solving for the speed, which means we need the frequency and the wavelength. Now the frequency I just gave to you in the problem is 2 hertz. Wavelength, you had to actually go out of your way and find it for this one. You cannot use the 6 meters, because that's not one wave. Like, I'm going to trace with my finger just like I did in that last lesson. I'm going to start at the top, go all the way down, back to where I started. This is one wave, which it looks like is less than the 6 meters. How many waves are in the 6 meters? I've got 1.5. Alright, so I've got 6 meters. What's going on? 6 meters. I don't want to split it in 1.5 waves, so I'm going to divide those, and when you do that, I think you get 4 meters. If you want to double check that, well, we've got 1 full wave is 4 meters, and half that is another 2, and the 4 and the 2 makes our total of 6. So we've got a wavelength of 4 meters. 2 times 4, I think, is 8. 8 meters per second. Our final answer. Alright, I kind of ran through that, but it's, a nice simple equation. We've been doing physics for 3/4 of a year by now. We should be okay with that. Wave transmission. Alright, transmission is when a wave changes medium. So if it goes from one thing to another, a wave changes medium. A nice example of that is like a light. If you look out a window, my window's over here. If you look out a window, light outside is traveling through air, and then it travels through the glass of the window, and then it travels through the air inside of the room. It changes medium. It goes from one thing to another to another. Sound can change medium. You can hear sound through solid objects, like it can move through the air and then through maybe a wall and then through the air again. So waves can change medium. There is one thing you need to remember about that. When a wave changes medium, when a wave changes medium, the frequency stays the same. So when a wave changes medium, the frequency stays the same. You just have to remember that. So when a wave changes medium, the frequency stays the same. But the velocity and the wavelength can change. So velocity and wavelength can can change. So the velocity and the wavelength can change though when that happens. And the reason it happens is this. This is because the number of waves has to be the same. Let's think about it like this. Let's say we have a change in medium. Like, let's go with the jump rope again. We looked at that guy jumping or doing the rope thing at the gym in our first lesson quite a bit. We had a wave, let's say we go through like, I don't know, maybe we're trying to take it easy. We have like a really thin string, right? And then all of a sudden we tie our really thin string to like a really, really thick rope. And let's say that, a thick rope is just fundamentally different from that thin string. They have different sort of properties. And so let's say the wave changes speed once it reaches that interface. Meaning, like, once it reaches this point right here, oh, it's still big. Once it reaches that point right there, it's going to change speed. But let's think of it like this. Let's say we send in 3 waves per second, which remember is it just hertz. Let's say I spend 3 waves into this like interface or this place where it changes medium. Well, how many waves are going to come out? Well, you send 3 waves in, then 3 has to come out. Like you can't send in 2 waves and get out 100, because where'd those waves come from? You're creating energy when you do that. That's not how physics works. In the same way, if you sent in like 10 waves per second, how many waves should come out? 10. So the frequency will stay the same, but the wavelength and speed can change. The speed just kind of depends on the like what it's made out of. So waves can travel faster through some materials than other materials. So let's look at how we would use that. 24. A mechanical wave transfers into a medium in which it travels with twice the velocity. In this new medium, what will happen to the wave's frequency? Okay, there's one thing I'm asking you to remember. When a wave changes medium, the frequency stays the same. So it's the same. Cool. Done. That's the facts that I would like you to remember. I'm not sure what we're doing for the test for this unit. I'll figure it out. But I can guarantee you that this will show up on it. So you gotta know it. When a wave changes medium, the frequency is the same. In this new medium, what happens to the wavelength? Well, I told you that can change. So we're gonna have to actually think about this a little bit. I know thinking's annoying, but what are you gonna do? Alright, we have an equation that'll help us out here. Because this equation references velocity and wavelength, and we know what happens to frequency. So it's like a really helpful equation. It's got all the things that we want in it. Let's think about how equations work. We know that we have twice the velocity. So the velocity is going to be 2 times as big. Right? I told you it's twice the velocity. And when you think about how equations work, this left-hand side has to be equal to the right-hand side. If they're not equal, that's not how equations work. This equals that. They're equations. They're equal. Alright, so this side must have gotten twice as big, because this side did. Did the frequency get twice as big? No. The frequency stays the same. Alright, well, if the frequency didn't get twice as big, then what must have happened to the wavelength? It must have gotten twice as big. So the answer here is 2 times as... we're going to say twice as long. So basically the wavelength, because of this, will always do whatever the velocity does. Like if the velocity goes up, that wavelength has to go up. If the velocity goes down, the wavelength has to go down. They'll follow one another because the frequency isn't changing. That's not like the variable here. Okay, that in mind, try 25, try 26, try 27. See what you can do. You can pause the video, give them a shot on your own. Alright, I hope you use that time to try this on your own. 25. Light is an example of a wave. When a light wave enters a glass block, it slows down. Explain what happens to the frequency and wavelength of light when it enters the glass block. Let's start with frequency. You should have answered that immediately. It's the same. Right? Frequency is the same. Whenever a wave changes medium, the frequency will be the same. But wavelength and velocity can change, so it's going to slow down. We have an equation to help us think that through. Alright. So I told you that it slows down. So this velocity goes down, right? It's going to be slower. Which means that this left-hand side of the equation is smaller now. Okay, well, this side of the equation is smaller than this side of the equation is smaller. Because again, that's just how equations work. Is the frequency smaller? No. Why? Because I told you. This was my explanation of it up here. But if you remember, just the frequency stays the same, you're good. So what must have happened to the wavelength then? That must have gotten smaller. So, what happened to the wavelength? Smaller. And that would be fine. That's a good answer. How can I make that question weird for you? Like, what's a confusing way I could ask it if I would, trying to prepare you for like a test or a Regents that no longer exists? Then we would 26 is a good example of that. A wave generator, having a constant frequency, produces wave fronts in a tank of 2 different depths. The diagram represents the wave fronts in deep water. As the wave travels from deep water into the shallow water, the speed of the waves decreases. Turns out waves travel slower in shallow water. In the diagram, show 3 lines representing appropriate spacing in the shallow water. All right. So we're changing medium here. Deep water, like the wave travels differently in deep water than shallow water. Specifically, I think it travels slower. So if I write out like a nice little v equals f lambda. All right, let's think our way through this, and yes, it looks very similar to the last one, at least for this part. The velocity goes down, so let's think about that wavelength here. Does the frequency change? No. So the wavelength must have gone down. And this one, it's kind of weird with this overhead view, but imagine like you're in a helicopter over the beach looking down at the waves. You'd see like, this is a wave, and then this is a wave, and then this is a wave as they go towards the shore. But now they're going to travel a little slower here, and so I think what you'll find is that these waves will be closer together. And you see how... Oh god. Oh, that's not terrible. You see how like this is the wavelength or the spacing between the waves that they kind of labeled for you right here? We're just going to make that smaller on these pictures. So here, again, just see that space is smaller. So as long as you drew these lines closer together, you did good. Last up, a mechanical wave with a wavelength of 6 meters and traveling at 30 meters per second changes medium, causing it to travel at 1/3 of its original speed. What's the wavelength in the second medium? Alright, well, let's think our way through this here. We've got a way of doing this. V equals F lambda. Oh, well, we're not going to write. Now we are. That's great. So we've got V equals F lambda. Alright, so what we're going to do is let's change color. We're going to take that velocity, we're going to make it 1/3 as big as what it used to be. Let's figure out what that does to the wavelength. Now, we'll start with frequency. What happens to the frequency? Nothing. I'm hoping you answered while I was waiting there. So which means that something must have happened to the wavelength. Specifically, if this side is 1/3 as big, then the wavelength must also be 1/3 as big. Alright, well, the wavelength used to be 6, so the new wavelength, well, 1/3 of 6 is 2. Alright, so the big idea there, when a wave changes medium, the frequency stays the same. If there's one thing you get out of this, that's what I want it to be. When the wave changes medium, the frequency stays the same. The velocity and wavelength can change, and they change with each other. Again, that one I want you to remember is that the frequency stays the same. Alright, last up on the... How long are we? Oh, we're good. Last up is sound. Alright, sound. A couple things that we need to know about sound. Sound is an example... I mentioned this earlier in the note packet, I think on page 1. Sound is an example of a longitudinal wave. This is a nice opportunity to review what that meant. So, what I'm showing here is an animation that I showed you already of the longitudinal wave. And this is really almost exactly what sound is, or what it looks like. All of these dots are going to be air molecules. And when something makes noise or creates sound, all it does is it just like pushes on those air molecules. So like, let's say you have a speaker or like a subwoofer. So this would be an example of a subwoofer, which is just the word for like those big speakers that produce a lot of bass. Like that like thumping sound, like when you hear like the beat from a song, is typically a subwoofer doing that. This would be one, like looking right here, that's turned like really loud and slowed down a little bit. And you can kind of see that all that it's really doing is it's just like pushing air. It's like a giant like basically cone of material. It just like pushes air forwards. So it just pushes air forward, so kind of like this red line here. And when it pushes air forwards, you've got these like little like areas of compressed air where you like smushed it together and pushed it really hard. And then when that subwoofer or that speaker retreats backwards, the air sort of expands behind it. So what sound is this longitudinal wave in which the air particles are moving parallel to the wave's velocity. So in this one, the wave is moving towards the right. You can see these compressions moving towards the right if you follow my mouse. And the individual molecules, if you just like pick one maybe along the bottom and you follow it, it looks like they just kind of move left and right, and then left and then right. Sort of back and forth. Here's that red dot that we isolated in that unit number 1. Kind of see it just moving back and forth and back and forth. And so that's what sound actually is. It's just these regions of high pressure and regions of low pressure. And that's how we actually hear things, which is really kind of cool here. So like if you go back. So like if you take like a speaker or something, it just pushes this sound forwards. And then when you hear it, it's those pressure waves, those like high pressure things. Basically what they do is they bang into your eardrum. So your eardrum is just like this little membrane thing that's somewhere in your ear. And what it does is it kind of pushes back and forth on this little thing that's somewhere in your ear called your cochlea. And it's just this little like fluid-filled thing, and basically it's these like longitudinal waves, like just jamming into your ear and pressing on it. And then your brain takes like that, again, that pressure, that pushing on it, and it turns that into sound. Like it can digest that and turn it into some sort of noise or music or vocabulary or whatever it is that's going on. So it's kind of neat when you think about it. It's just this like air pushing on your ear, and just that composes all of the sounds that you hear. So sound is an example of a longitudinal wave, is I guess the moral of that story. It's a longitudinal wave. Now, you hear different things about sounds. What I mean by that is like you hear high volumes and low volumes, and like high pitches and then low pitches. So for sound, the amplitude is related to the volume. Meaning, high amplitude equals high volume. So if you wanted to listen to this video at like real high amplitude, lots of energy, you would just turn up the volume on your speaker or headphones or whatever it is that you're using. So amplitude is related to the volume. Yeah, great. Frequency is related to pitch. A high pitch is equal to a high frequency. High pitch, high frequency. So like if you play an instrument and you're playing like a high note, like a high noise, like a soprano, what you're doing is you're playing like a higher frequency of sound. If you have like a bass or like a lower pitch, then that's just a lower frequency of sound. So essentially, those you see these little compressions that are hitting your ear? If they hit your ear very frequently, like very quickly, your brain turns that into a high pitch. If they hit your ear less frequently, your brain like registers that as a low pitch. So that's kind of like the differences that you hear between these sounds. Actually, can I do this or no? So if we look at a couple different frequencies, this is something I would normally do in class. I don't know if it's going to work as well, but through the speakers. But so I'm going to play a frequency of 440. If you play an instrument, you know this as a concert A. It's like or if you've ever like seen an orchestra concert, it's like when the violin gets up and plays a note to tune the whole orchestra. This is the note that they're playing. It's called a concert A. And I'm sorry if this is a little annoying in your ears. Okay, that seemed loud to me. So that's what we call a concert A, 440 hertz. Now, if I increase the frequency, which I can do by just sliding this up, notice the frequency right here, measured in hertz. Notice as I increase the frequency, we're going to hear a higher pitch. Oh no. Oh my god, I'm so sorry. So or, if I go the opposite, I'm going to lower the volume a little bit. If that'll help. If I lower the frequency, we'll get a lower pitch. And so that's what you're hearing when you hear different frequencies. Again, this measured in hertz is how many, there's a sound hitting your ear a certain amount of times per second. Your headphones right now, this is very low, might not even be able to register the 70 times this sound wave is hitting your ear. But if you go higher, I'm sorry about this. Now it's hitting your ear 311 times per second. And your brain just kind of turns it into a higher pitch, that higher frequency. Alright, I really apologize if that caught you off guard. Back to our notes. So, yeah, that's almost everything. And then the last little bit I have to add is the speed of sound. The speed of sound is affected by the temperature and pressure of the air. At STP, which maybe you remember from chemistry, standard temperature and pressure. The velocity... I'm sorry. The speed of sound is 331 meters per second. Now you do have that in your reference tables, which means that I'm just going to tell you that the atmosphere is at STP and assume you know what that means. In your reference tables, since it's a constant, it'll be right on that front page, right below the speed of light, which we used earlier in this lesson. The speed of sound in air at STP. They did write it in scientific notation. I'm not sure why, because 331 is easier to look at than 3.31 times 10 to the second. But I'm going to tell you that it's at STP and expect you to look this up in your reference table for a problem. Okay, so for now we're going to start with I'd like you to watch this video right here and then answer the questions that go with it. I'm going to go over the questions in a second. But watch the video, and see what you can do with this. Yeah. All right. So I'm hoping by now you watched the video and answered the questions. Just to go through this really quickly. At the start of the video, a ringing bell was placed inside of a jar, and after 11 seconds, the person recording the video turns on the vacuum pump, which removes air from the jar. What happens to the volume of the ringing as the air is removed? I'm hoping that you noticed it went down. It decreased. Let's go decreased. Why does this happen? Well, we just said that sound is vibrating air. If there's no air, there's no vibrating air, right? Because there's no air to vibrate. And if there's... And that's what sound is, right? It is that vibrating air. Now, the best sort of physicsy word I would use for this is, why does this happen? Because there's no medium. It's like the best answer I would like to hear there. Because, again, medium is what this mechanical wave travels through. All mechanical waves require medium. Without this medium, the wave doesn't even exist. Without air, vibrating air doesn't exist. And that's what sound is. B. At the 1 minute 20 second point of the video, the person allows air back into the jar. What happens to the volume of the ringing as the air returns back into the jar? I'm hoping you noticed that it got louder. The volume increased once we let the air back in. Why does this happen? Because there is a medium, right? Because there is a medium. So just trying to bring up this idea that sound is this vibrating air, and without air, there's nothing to vibrate. There's no sound. We'll do number 2 because that's a good calculation one, and then I want you to try the rest on your own. Sound has a frequency of 261.6 hertz. So I'm just going to write this on the side. F equals 261.6 hertz. What is the wavelength? So we're solving for lambda. Lambda equals question mark. Of this sound at STP. Alright, well. So, doesn't seem like we have a lot. Frequency, wavelength. I am hoping that you think to yourself, alright, well, it's a calculation question. Let's go to the reference tables and the wave section. And there is an equation with frequency and wavelength in it. Again, we've only covered these 2 equations for this topic, these first 2, so you don't have to look through the whole thing here. I'm looking at V equals F lambda. It's got F, it's got lambda. The thing is, it also has this V in it. And I don't think I mentioned the velocity looking at this question, but I did say it's at STP. And I said, what was it, like a couple of minutes ago, that the speed of sound at STP is on the reference table is 3.31 times 10 to the second, which is 331 if you turn it out of scientific notation. So let's add that in. V equals 331 meters per second. And if you catch on to that, this is a very easy question. V equals F lambda. 331. I'm not going to show my units because I don't feel like getting full credit, and there's no regions anyway, so whatever. Equals lambda, and we got to solve for this wavelength here. And when I do that, I got 1.26 meters. So what that really means is that if you look at a sound wave, again, it's those compressions and expansions. So let's freeze this animation right here. The sound wave is these compressions and expansions. The difference between one to the next one is 1.26 meters. That's how far apart they are. That's our wavelength for these longitudinal waves. Okay, from there, I'd like you to try numbers 4, 5, 6, and 7. Pause the video, try them, and that's going to be it for this lesson. So, I'll walk through the answers in a second, but take a minute to try these. Okay, I hope you use that pause to pause the video yourself and try all of these. And now we're going to go over them. Why is there no sound in outer space? Well, in outer space, there's no air, right? You can't breathe in outer space, there's no air. Which means that there is no medium through which sound can travel. So, kind of weird in outer space, like if you were standing, if you were like 20 feet away from a massive explosion or like some crazy event, you would hear nothing. It would be completely silent, because there's no, if sound is vibrating air, there's no air to vibrate. There's no sound in outer space. 4. The sound wave produced by a trumpet has a frequency of 440 hertz. Okay, writing down a bunch of the things that we know already. We've got a frequency. What is the distance between successive compressions? Okay, that's a weird way of phrasing this, but remember, sound is a longitudinal wave. So we got a couple close together, a couple far apart, a couple close together. When I say compressions, that's the close together part. So I want the distance from here to here, which is just a weird way of saying the wavelength. The wavelength just kind of looks a little different for these longitudinal waves, because longitudinal waves look a little different. And I mentioned this STP thing. And once you see that STP thing, you should think to yourself, like, that sounds kind of familiar, like something I'm supposed to look up in the reference table. And sure enough, the speed of sound at STP is 3.31 times 10 to the second meters per second. Which again is just 331, so I'm going to go with that. So we know V equals 331. So this should become like kind of like red flag's the wrong word, but like a good flag. Like a clue that this is what you're supposed to be using. Good flag. So I'm going to use V equals F lambda, because we know V, we know F, we're solving for lambda. We know that V is 331, because again, that STP thing is really a giveaway that this is what we're using. I'm going to leave out my units again. We've got 4. No, that wasn't it. We've got 440 hertz. We're solving for lambda. Divide carefully. I think you get 0.75 meters. I rounded a little bit there. Cool. A student observes a lightning strike. So you see lightning. So this there's a separation of 5 seconds between the flash and the thunder. So, like, when you see the lightning flash, like, how you see it flash, and then a couple seconds later you hear it, like there's a delay. That's what we're talking about here. There's a 5-second delay. Assuming the atmosphere is at STP, how far is the student from the lightning strike? So we want to know how far away the student is, but that may or may not be a wavelength. So we're actually not finding the wavelength. We're finding, it sounds like a distance, right? Like how far you are from something. I did say STP, and we know the sound travels at 331 meters per second. And I gave you a time of 5 seconds. Well, V, D, and T, I'm hoping sounds like really familiar. It was the first equation we did this year. V equals D over T, because I did say that waves travel at a constant velocity. So most of the time we're going to use V equals F lambda, but maybe this will show up every once in a while. Be on your toes. Over 5. Alright, I'm going to multiply across. When you do that, you get an answer of, I got a distance of 1655 meters. So it's kind of like not an old wives' tale, but like the saying goes, like if you see a lightning strike and you start counting like the seconds that go by, like 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. For every 5 seconds that goes by, that lightning strike was 1 mile away. If you run track, you know that 1 mile is about 1,600 meters, which is pretty close to what we got. So actually, this kind of works here. If you see a lightning flash and you count to 5 Mississippi, 5 seconds, that lightning flash is about 1 mile away from you. If it's less than 5 seconds, it is less than 1 mile away. And if you count more than 5 seconds, it's more than 1 mile away. Kind of neat. Something you can figure out there. 6. A subwoofer puts out a low-frequency sound wave of 50 hertz. What's the wavelength at ST? Okay, as soon as you see this at STP, I'm hoping it's like the third question in a row. You went for the V equals F lambda. We know that V is 331 at STP, and why do I know that? Because it's right in your reference tables. Equals, we know the frequency is 50 hertz. This is kind of a lower frequency, so we're going to get a bigger sort of wavelength here. And sure enough, you get a wavelength of 6.62 meters. This is probably a little bit below the range of human hearing. If this was if the sound is being played, you probably wouldn't be able to hear it. Your ear just doesn't work at that low of a frequency. Last up, number 7. A sound wave with a frequency of 440 hertz is traveling through a tube as shown. Okay, so remember, we've got these compressions, expansions, compressions, expansions, compressions. So I'm not going to give you like the transverse wave squiggle. I'm going to give you this longitudinal wave looking thing. What is the wavelength of this wave? Well, a wavelength is from one point of a wave to the next time it occurs. Right? The complete cycle. Just the complete cycle looks a little different here. So it's going to be from a compression to the next time a compression occurs. I'm counting 2 wavelengths here. Like we've got 1 and then we've got 2. So 1.5, cut that in half, you should get 0.75 meters. But you did need to calculate the speed of the wave. We are not at STP, so it might not be exactly 330. It shouldn't be far off, but it won't be exactly 330. So let's see what we get. We know the equation for the speed of a wave. I gave you the frequency is 440 hertz. We know that the wavelength is 0.75 meters. Multiply that in your calculator, you should get 330. So again, close to that STP value, but maybe a little off. Maybe it's a little hot that day, or there's a low pressure system moving in. C. What type of wave is this? Okay, you have to know this. Sound is a longitudinal wave. How would you know that? Because you should have written it down earlier. So that's a fact you got to remember. Sound is a longitudinal wave. All right, that's it for this one. Thanks for hanging in there.